All right. Hello, everyone. Happy Tuesday. My name is Heather Grant. Welcome to today's webinar. I'm really excited to kick us off today. I work as one of the maintenance community admins for the maintenance community on Slack by UpKeep. Thank you for being here with us today. If you are not already a member with us in the maintenance community on Slack, we would love to have you join us. I will drop that link on how to sign up in the chat in just a moment. Today we have James from Eruditio joining us for a presentation on design for maintainability. Should be really interesting. I'm excited to learn a lot. The recording from our session today, as long as a copy of the slides you see here, will be available in the maintenance community on Slack tomorrow. The recording also does go live right after we end our session, so you'll be able to access that at the same link. James himself also is available to answer questions live in the Slack group, so please feel free to share the recording of this webinar or the invitation to Slack directly with friends or colleagues or anyone else you know who would benefit from hearing some of James's expertise. My last piece of housekeeping, and then we will go ahead and get started. You'll notice that your cameras and microphones are not turned on today. So what you'll do if you want to ask or answer any questions of James, you will use the chat feature on the right-hand side of your screen there. Feel free to pop in, say hello, let us know where you're joining from as well. We will work on answering questions as well as we can throughout the presentation, as well as time at the end. But any questions we don't get to, we will answer offline in the community. And that is it for me. Thank you again, James, for being here. Thank you, everyone, for making the time to join. And James, I will hand it over to you to get us started.
All right. Thank you. All right. Good morning, afternoon, or evening, depending on where you are. Thank you for joining today. For those of you that I have not had the opportunity to meet or work with before, my name is James Kovacevic. I'm a principal instructor with Eruditio. Been involved in maintenance and reliability for almost 17 years now in various aspects. Spending a lot of time working across the globe, different industries. I've spent time in the Middle East. I've spent time in South America, Africa, Europe, Asia, and of course North America, working on delivering maintenance and reliability programs for organizations. Myself am based in Canada, so you might hear a little bit of the Canadian accent come through, but don't hold it against me. Aside from that, I have a weekly podcast rooted in reliability where we bring in experts to talk about all the different topics within maintenance. And more recently, I actually participated in co-authoring a book called Design for Maintainability. We're going to talk a little bit about that today. As Heather mentioned, if questions come up, feel free to just throw them in the chat box and I'll answer them as best as I can as we're going right through the presentation, and then we'll have some time at the end as well to answer any questions that come up. All right, so let's get started. What is maintainability? Well, maintainability, some people relate it to MTTR, or mean time to repair. And that is one type of measure of maintainability, but the true definition of maintainability is a little bit different. And that is, what is the probability that the maintenance work will meet established intervals on time? So what does that actually mean? What it means is if I have a 4-hour window to perform this repair before it starts impacting downstream operations, impacting deliveries to customers, those types of things, what's the probability that I'll be able to execute that repair in that 4-hour window? Or if we're in something like aviation, for example, or we're at a port and we got to make sure that we're managing those cranes in the appropriate time, we can use this to also calculate what's the likelihood we'll get our preventative maintenance activities done in that allotted downtime period. All right, so maintainability is, what is the probability that we'll be able to do our work in the allotted time? That's what we're really trying to do. On the screen, you can see there's a couple examples here of the different calculations that you may have. And as an example, if we walk through a basic example here where we have an MTTR of 12 hours and we have a 4-hour work in progress buffer. For example, we have 4 hours that we can continue to operate the site before we shut down this facility based on a repair. What's the probability we'll get all that work done in that 4-hour period? Well, in this example, with a maintainability window of 4 hours, the probability of being able to do that is 28.35%. So if we decrease that MTTR, our probability will go up. If we increase that 4-hour window, our probability will go up as well. right? So there's a little bit of a relationship there, and we'll get into a little bit more of that as we go. Now, there's a lot of other things out there. Reliability, availability, maintainability, all these things people use, and sometimes they're not exactly used as they were truly defined and intended for. So I want to kind of clarify those, what they are, and then we can talk about how they relate to each other. So reliability, that's measuring how reliable is that equipment, and the true definition is the probability that a system will perform its intended function for a specific period of time in a specific operating context. So what does that mean? We have a crane that we need to operate for 12 hours without failure. All right, so we got our specific time period, 12 hours, in a specific operating context. If I'm up in the high Arctic, that crane may react differently and behave differently than if it's in the desert. So therefore, we need to include those specific operating contexts as well. And that's probability that will make that 12-hour period. Now, availability is a little bit different, and that's the probability that an asset is capable of performing its intended function when needed in a stated environment. Much simpler to calculate availability than reliability. And then maintainability, we've already gone through that in detail. Now, why does this matter? Well, there's a relationship between them. All right, if we see when we don't have an asset operating, we're measuring mean time to repair. If a asset's operating and then it has multiple failures, we're measuring the mean time between failure. Now, those are means, so they're an average time to repair, average time to repair, and average time between breakdowns. All right, but they have a big impact on what availability is. So if we take a look at some of the basic calculations for availability, these are the three main ones you typically see. AI, which is inherent availability, that's really only looking at mean time between failure and mean time to repair. Failures only. All right, that's from a design perspective. We can look at operational, MTBM over MTBM plus MDT. MTBM, mean time between maintenance, any maintenance activities. That could be corrective or preventative activities. And then mean downtime is from when the equipment stops operating to when it comes back up. All right, that's operational availability. Then achieved availability is a little bit different. It's still mean time between maintenance activities, but we're also looking at mean active maintenance time, which means hands-on only. All right, now why this is important is theoretically, inherent availability is a design product, does not include downtime for preventative maintenance, and that is the highest level of availability you get for a given asset. Operational is the lowest. Operational says from the total time we're down for whatever reason for maintenance, that's being counted. Whereas achieved shows what can be achieved in a given organization. Now, the difference between achieved and operational is logistical delays. Operational includes those logistical delays of not having parts, not having the right equipment, not having people in the right location, where achieved rules all that out and says, if we have everything where we need it, this is what we're going to have. All right. Now, maintainability feeds into a lot of these. So we typically will measure maintainability from an MTTR perspective or a mean active maintenance time, something of that nature. And designing for maintainability really allows us to drive improvements in all levels of availability, which is what we want. We want our assets to operate. All right. As an example here, you can see there's a couple different examples. If we have different varying levels of MTBF, MTTR, what's going to be that impact on availability? All right. So there's a lot that goes into this, but we want to focus mainly on the maintainability side for the rest of this conversation today. So why do you need maintainability? I'm sure all of you on the call have dealt with these types of things before. All right, now these types of things that I'm referring about is you have to replace a pump, but you can't get a lift truck in there. You can't get a crane in there. You can't do anything. So now you have to fabricate some way of lifting up and moving this pump. All right. Or you've ever had to, contort your body in some awkward position to try and reach up and access a bolt or something of that nature. Right? That's because we're not considering design for maintainability there. One of my favorite, you have a machine stop. There's no faults, no errors, there's no flashing red lights. You spend hours doing it, and what do? You end up powering it down, powering it back up, and guess what? It works because you cleared whatever that fault was. But it never told you there was an issue. All right, so that is maintainability as well. What built-in testing do we have? What built-in prognostics do we have? That is maintainability. Then, have you ever installed a new machine but had no PMs, no spare parts, specialty tools to maintain it, missing all the different things you need to do to maintain this asset, and you start learning it the hard way? Once again, that's why you need maintainability. You need to be able to address all these different pieces in the design phase, so that when we get the asset, we can actually work on it. We can support it. All right. Now, maintainability definitely needs to start early in the process. All right, we have to start early. We can't start considering maintainability once the asset's already built and installed. There's certain parts of it, like supportability, that we can improve, but we're really limited in what we can do at that point. Now, this graphic here illustrates the life cycle of an asset. You notice the yellow here? This is the money we're putting out at the various stages of acquiring an asset. So conceptual design, demonstration, validation, engineering, manufacturing, construction, then production, operation, and salvage at the end. We notice early here that in reality, we're in the design phase, we're not expending a lot of money with that asset yet. But we can be committing to 50 to 60% of the life cycle costs in that phase. And our opportunity in this white dotted line to influence life cycle costs goes down dramatically as we get further into the stages. So if we want to have a huge impact on maintainability, we have to do it early in the design phase. Now, it's said that from Paul Berenger, for those of you that know him, that roughly sustaining costs, so this production salvage area here, is 2 to 20 times more than the initial procurement costs of that asset. 2 to 20 times. That's huge. So what can we do to impact that and reduce it? Design for reliability, design for maintainability. Now, I'll give credit where credit is due. The defense industry does a very good job in these early stages here for looking to reduce maintainability costs, reliability issues, and really driving down life cycle costing. Defense industry does that well. Most manufacturing industries don't do very well in that area. And as a result, we have a lot of the problems that we do. So let's talk about how we overcome these. There's a bunch of elements of maintainability that we want to consider when we start designing for maintainability. The first is part standardization. Right. Many of the storerooms I walk into, they have some Allen Bradley PLCs over here. They got some Siemens PLCs over here. They got some old Modicon PLCs over here as well. What is that doing to us from a maintainability standpoint? It's really hurting us for a number of reasons. One, we got to stock a lot more parts now because we have 3 different PLCs. Not only do we have to stock more parts, there's a lot more effort that has to go into training now. Instead of our staff being able to work on one PLC like Allen Bradley, learn the software, learn it well, they got to be generalists at all 3 now. We also have to have different software for those examples there. So we got training, we got software, we got the number of spares. And in some instances, we may have different specialty tools and different modules and all these other things we got to do if we have all these different parts. So part standardization is a huge piece for maintainability. How can we be consistent in that? Then there's modularization, all right? And the best way to explain this one for you is, what can we make modular? A light bulb is a great example. I can put different wattages of light bulbs in there. I can put different types. I can put a traditional incandescent light bulb. I can put a LED. I can put a compact fluorescent light in that same socket. Where can we modularize these things? Whether they're access panels, whether they're circuit boards, and so on and so forth. We want to modularize it as much as possible. Good question. No, we should identify those hard to access points throughout the entire life, but our biggest ability to impact those hard to access points is in the design phase, Rupesh. If we can identify them early in the design phase, you actually have the ability to influence and address those issues before they become an issue that you have to overcome. I'll give you an example. I worked for a company once upon a time, and we built a brand new facility. We never did a design review, so we never looked at hard to access points, those types of things. And as a result, we were finding these things as we were working through the facility after it was already built, and spent a tremendous amount of money putting in platforms, lifting points, all these other things after the fact. Right? We built another facility a few years later, and there was lots and lots of design reviews. As a result, we were able to identify all those different issues, get designs changed, stuff moved, and we were able to maintain the facility a lot easier. You have the biggest chance of influencing it early on, but you'll identify all those hard to access points through regular job planning and so on and so forth throughout its life. From a kit packaging, moving on to the next element, the kit packaging is pretty much job kitting. All right, how do we kit jobs? Not only from a planning and scheduling standpoint, but identify kit packages. So you have one part number that has all these sub part numbers in it. So when we order that, we have everything ready to go. Part interchangeability is another important thing. Easiest way to explain this, avoid custom sizes. If you have to build custom sizes, shapes, fittings, etc., that becomes a problem. So use commercial off-the-shelf parts where possible. Human accessibility, we got to provide that adequate room and space for the maintainer. If not, there's a risk of excess time, safety issues, and so on and so forth. Now, fault detection and fault isolation, two very important parts here. So fault detection is how do we detect a fault with the system? Sometimes visually is best, and many of the more complex assets we have built-in fault detection systems, whether they're warning lights, whether they're fault logs on an HMI, and so on and so forth. But we need that to be able to restore that asset quicker. Building on that, once we actually identify a fault, how do we isolate it so we can improve troubleshooting speed and improve the response to those issues, that sort of thing? I'll give you a great example. There's been some machines I've worked on that if a gate switch is open, it'll tell you gate switch open. And as a result, you can't operate that equipment. So now the maintainer has to go around and check all the different gate switches. And depending on the size of the machine, it may only take a few minutes or it may take quite a bit more. Fault isolation would actually tell you which gate switch is causing the problem. All right. So we want to have these types of systems built into our assets to improve maintainability, make it easier to troubleshoot, repair, and so on and so forth. Part identification is last. All parts should be numbered one way or another so we can figure out what this part actually is and identify it in the storeroom and the drawings and really get that unordered or get it out of the storeroom quicker. This really helps with reducing downtime and ramps up the learning curve for new maintainers. All right, another question, how to overcome single sourcing for part standardization? It's very, very difficult. There's quite a few equipment manufacturers that I've used in the past that always go to Siemens, for example, but the organization wants Allen Bradley PLCs. So what they'll have to do is often negotiate some of that, and usually it comes at an increase in cost for that asset. That's where we'll get into weighing cost versus benefit in some of these design trade-offs, and we'll cover that in a bit. All right. Now, there's a couple other paradigms of maintainability we're going to chat through. All right, maintainability is inversely proportional to reliability. As reliability goes up, maintainability generally goes down. Less system faults occur, have to spend less time doing maintenance actions. All right. Maintainability is also related directly to testability and prognostic health management. Really, how well can we identify and isolate those failures? The more we improve that in the design phase, whether PLC logic, fault detection, those types of things, the more we can improve maintainability. Many of you are already aware of this, but as we move from scheduled maintenance to condition-based maintenance, we'll improve maintainability as well. We also want to make sure we consider the human as the maintainer, not just with the space and design, but the need for tools, specialized training, and so on and so forth. The more the equipment is designed with the maintainer in mind, the more likely the repairs will be completed in time. Think of the skill level of your maintainers. If they're all very, very well trained, very, very highly educated, we're going to be able to do different things to reduce the need for some of this maintainability stuff. But if we're in an instance where we don't have very highly skilled, highly educated maintainers, we're going to have to put more into that equipment to make a major shift in maintainability. We also have modularity. All right, what do we mean by modularity? Quick connects, plugs, connectors, those types of things. We want to reduce the need to manually unwire cables or unsolder cables and resolder. Connectors, plugs, etc. speed up that maintainability time. Maintainability predicts downtime during repairs. If we did a very good job at design for maintainability, we should be able to predict what amount of downtime we're going to have for not just the asset, but for individual tasks and so on and so forth. And we'll talk about a couple examples of that in a bit. But in order to do this all, you need to understand the maintenance requirements, right? You got to understand, where is this asset going to be used? How is it going to be used? When is it going to be used? Often, a lot of organizations have some pretty generic requirements and they don't get into these details. And as a result, we have failures that are being introduced because we miss some of these critical requirements. Whether you're speccing a machine or designing a machine, you need to make sure those requirements are clear and you spend a lot of time on them. And then lastly, maintainability has to be supported with data. We'll look at tools like FMEAs, level of repair analysis, life cycle costing analysis, and those various things. And those are all going to help us influence design considerations for maintainability. All right. Now, let's get into some of the practicalities of this. So, design for maintainability, it is a challenge. We have a bunch of things we need to consider and balance. Economic trade-offs. Do I want to spend a little bit more upfront for less life cycle costs? Or how do I strike the balance if I have 3, 4, 5 different options? Which one is the best one, short-term and long-term? Right? Maintainability is a cross-functional activity. You can't just have design engineers doing this. You need someone who knows maintainability, who has been a previous maintainer. You need the reliability engineering team in there involved as well. And it's an iterative approach. You're going to go through these designs and reevaluate and update and reevaluate again and so on and so forth till we get something that meets our needs, the system requirements, as well as the economic requirements. The way you typically see this happening in organizations is, first, we have the design requirements. What are the system requirements? The large overriding requirements. The operational, functional, performance requirements. So if we have a widget machine that has to produce 300 widgets per minute, we have to be able to identify that, but then also identify, is it running 24/5, 24/7? If it's 24/7, when do we get maintenance opportunities, and so on and so forth? That's all in that requirements phase. Once we have that, then we can come up with an initial design and do a design analysis. And we want to compare that design against all of these requirements. And we're going to use various tools like maintainability allocation, predictions, and so on and so forth. From there, we're going to take all that information we learned and we're going to go back and redesign, refine that design based on the feedback from the analysis. And then once we get to a verification standpoint, we're running our design through various models to say, yes, it's going to meet all these design requirements. But we're not done there from a maintainability standpoint. We also have to be considering supportability. How are we going to support this thing once it's in the field? What maintenance programs, what spare parts, what training will be needed to ensure that this asset does what the customers want? Right? And that's really the high-level process for design for maintainability. So, Rupesh, yes, there's a lot of machines that have very little room for maintenance. Honestly, I don't see that going away. But what I do see happening in some organizations is they're spending a lot of time with their vendors to identify those specific problems. And even if it's a little bit more upfront cost, making those design changes, because they realize making some of those design changes now will have a huge impact when it's fielded, making it easier to maintain and so on and so forth. I don't think it's ever going to go away, but there's opportunities to improve it. Think of drones or fighter aircraft or stuff of that nature. Very, very compact designs, but yet they're able to maintain them fairly easily. Whether it's access panels located in various locations, modular components where they can swap in and out easily, those types of things. So there's still things we can do there. We might not get away from it, but we can still have an impact on it. All right, but maintainability, or design for maintainability specific, is all about trade-offs. None of us have unlimited budgets, so we got to perform trade-offs using life cycle cost analysis for various specifications. This is just a brief example, But here we have three options that we can propose in this design for this system. One is a single pump, one is a dual pump, and one is an upgraded pump. All right. What we're doing here is we're comparing what is the initial cost versus the long-term cost of this asset. We can see here that the one pump, much cheaper to purchase up front, but as we go on in years, it becomes much more expensive. The one upgraded pump, a little bit more expensive up front, but a little bit better long-term performance than that single pump. But the dual pump, midway between for initial purchase cost, but long-term, it's the cheapest. Why is that? We can go in and we can deep dive using some of our tools here and see that the lost gross margin is the biggest differentiator there. We're running two pumps. We're improving availability through redundancy. All right, so that one there is a trade-off. We've got a couple different options here. We got an extra asset to maintain. So these are the types of trade-offs that we're going to do as we're going through all the different variations and options within a design. Some of the other stuff we may be doing for design for maintainability is something called allocations. Right? If we have a system requirement of being able to maintain this asset with a mean time to repair of 3 hours, right? We can do something called allocation, which means we take our system requirements and we break it down to subsystem requirements. We break down those subsystem requirements to component requirements. Right? Now, we also need some reliability data for this to run the analysis. But if we take a quick look in this example here, we need an MTTR of 3 for these 4 blocks here. Well, you can see one has an MTTR of 9, one's got an MTTR of 5, 3, and 2. But you can also see our failure rates here. And that's 10 to the minus 3 is what we typically use for the failure rate time here. So you can see we have all our different failure rates here. And if we go ahead and plug it into a little formula, we've got our failure rates, we got our mean time to repair. Now we got K. This is our allocation factor. Normally that would be an allocation factor of 1. All right. And that would give us what our mean time to repair is for that system based on failure rates. So how much downtime are we expected to have over that period of time? What the allocation factor does is allow us to look at this system and say if we improve it or reduce our MTTR by a certain amount, how much do we have to reduce it to be able to get there based on failure rates? So our allocation method for this is 0.95, meaning as long as we're delivering 0.95741 from an allocation factor, we'll be able to hit our maintainability goals of 3. You can see overall it ends up being 2.99 MTBF. If we left this as an allocation factor of 1, we would actually end up with 3.13 MTTR. Right. This is a very basic, constant, or equal distribution method. There are much more complex methods for doing allocations. They have failure rate complexity methods, which really means the ones that fail more often, we're going to spend a lot more time on those unreliable parts and pretty much ignore the ones that are more reliable. There's also statistically based allocation methods and a few others if you really want to get into it. But what we're really trying to do here is figure out what components do we need to focus on reducing that MTTR, and then how much do we have to reduce it by to give us our ultimate goal from the system requirements. Some of the other goals that we have, or other tools that we have, is a design FMEA. All right, so as we do our design FMEA, we want to consider all the different things that can go wrong with this design. Is there difficulty in diagnosing this? So if our detectability has a very high risk, what can we do from a design perspective to improve that detectability? All right. If the severity is quite large because spares availability or location of those spares, those types of things is going to be an issue, then how do we address that? Is the severity going to be high because of accessibility to equipment or components? That might be it. Is there a risk of something failing due to infant mortality and having to repair it because we need special tools, special resources, those types of things, complexity of repair, all those different things we want to address in here. This is not just how do we maintain this thing better. It is how do we identify all the different ways this asset is not going to do and meet those system requirements, and what can we do about it? And it's also looking at the supportability, not just the design phase. Some of the other stuff we have is we have maintenance task analysis. Now, maintenance task analysis is really going through and identifying what do we need to do for every single maintenance activity on this asset. All right, and that can be a variety of things. That could be corrective actions, preventative actions, calibrations, and so on and so forth. But the way we want to do it is we want to define the system, the specific item or component that we're working on, maintainable item, and the task. Then we define the frequency, the steps for that task, personnel requirements, spares requirements. Then we're going to repeat this over and over on all the different tasks. Then we'll consolidate the task findings in a larger overview, and I'll show you an example of walking this through in a moment. We'll also have to define what facility requirements. Is there any packaging, handling, transportation requirements? Is there specialized test equipment? We identify all these different things to make sure that when this asset gets deployed, wherever it is, we're able to support it. Now, we can also do this in the design phase, and once we summarize and finalize our analysis, go back and recommend design improvements. If we're not going to go back and do that, then we procure the logistics and support elements, and I'll walk through an example. Task level analysis here. We're going to troubleshoot item 1, replace item 1, calibrate item 1. Those are each different tasks that we're going to do. So each one would have its own task analysis. We'd summarize all that for what does it take to maintain item number 1. And once we do that across all the different maintainable items, do we meet our asset requirements? All right. Now let's walk through an example to make this a little more practical for you. Here we have an example of having to replace a number 2 seal water pump. All right. So you can see here, we have a coupling that we're going to be replacing on the number 2 seal water pump. What's the parent system? Description of the maintenance. So the coupling has been found to be damaged or displays excess wear. We got to remove and replace. Okay. What's the component and task number? So we can reference this to all of our procedures and documentation. Move and replace. What level of maintenance are we going to do this? Is it organizational or intermediate? And we're going to talk about that in a moment. But organizational is your frontline staff. Intermediate might be a depot or specialty support group. And then the depot level is very, very specialized. And we'll talk about that in a bit. And then our frequency and task. From here, we list out all the different tasks, task duration, frequency, and then what skill level do we need? Basic or intermediate or experts? And you can see here how we break that out. So now we know how much people do we need, what skill level do we need of these people, and so on and so forth. It's the first step. Once we have that, then we got to look at what are the other things we need to support this activity. All right. Here you can see on step number 0050, we need a shaft. We might need a torch on this kit. We might need a coupling and shim pack, a guard, an alignment kit. All right. These are all the different things we have to identify in the maintenance task analysis. Our replacement parts, our test, support, and handling equipment, and then lastly, facility. Do we need a specialized facility to maintain these things? Is it a machine shop? Is it a dry dock, for example? It could be all these different things that we want to consider. So we would do this for each individual task as well. From there, we move on and we summarize it in the items sheet. Here you can see the different component task number, all around that coupling, remove and replace, inspection, align and adjust. What levels, what's the frequency, what's the task time, the skill levels, the personnel time, part requirements, test and support equipment. You can see all that's laid out there. And that's just at a single item, a coupling. We would do this for all of the other components. The idea behind this, one, you know all the different parts you're going to need. You know what your personnel requirements are going to be for that asset. You're also going to identify all the different specialty equipment you may need for that asset. All right. Major plus of this is, if you do this up front, your planners will be refining these, not developing these from scratch in the long run. All right. So one tool we can use to identify maintainability options. If we have a lot of stuff here that says untested equipment, cranes, specialty equipment like that, then we can identify how do we address this? How do we build in something so we don't have to bring in specialty cranes and other tooling for that activity? The other thing we want to consider, human factors analysis. Can our people actually work on it? So here's a basic graphic of some of the different spacing requirements you need for the average person to work on equipment. But that's not the only thing we want to consider, all right? That's, part of the anthropometric factors that relates to the size, strength of the operator or maintainer. That's really looking at, can they fit into that space? Can they reach it? Are they strong enough? That sort of thing. Those are some things that we want to consider. But we also want to consider some of the other factors when we're talking about maintainers. And one is the human century factors, all right? Can they see, hear, feel, or even smell what's going on around them? So for operators or maintainers, Can they actually read the instruments and control consoles easily? Can they identify or work in tighter nooks and crannies without needing flashlights and things of those nature? Right? Ambient noise levels can also impact some of that, so we want to consider that. Physiological factors. Are there environmental stresses that will affect human performance? Once again, if we're in the high Arctic or the desert, there's different environmental stresses that may impact human performance, and that may impact some of our repair times, our maintenance times. All right, we want to be aware of those. And then there's the psychological factors and how people make mistakes. So is it a slip or a lapse? Is it a mistake or violation? So intended versus unintended errors. So Poka-yoke is designed to eliminate some of those unintended errors. Those are all important design considerations. We need those things built in to make sure that we're not introducing failures and mistakes into the machine, into the troubleshooting process, and so on and so forth. All right, great question, Francisco. How much data or time can we consider to allow us a good, reliable study? I'm going to say it depends on a lot of factors. One of those factors is going to be your organization. If you're building a one-off machine, I wouldn't expect to see as much of this type of study done. I would expect to see a much higher level review. If you're working in an organization where you're building fleets, hundreds, thousands of these assets, then you're probably going to spend a lot more time on it. In the back, we'll get to some quick things you can do, even if it is a one-off asset or it's not something you do very often, of just questions to ask. So how much data or time? That's going to vary dramatically. If you have a specific situation, be more than happy to chat with you offline about it. All right. So then comes the next big piece, which is supportability. How do we support our asset once it's actually deployed? Now, ideally, we're doing this before the asset is even on site. All right, this is, well, it's still being developed, whether our vendors are making it, and so on and so forth. We want to do these types of things to understand what do we got to do to make sure we can actually commission and operate this thing when it shows up on site. Supportability analysis takes a lot of different information. We might be doing a level of repair analysis or a maintenance task analysis or RCM or FMEAs. We have all these other data sets coming from some of the design review stuff. And from there, we're going to design what we need to do to support this asset. Right? We want to make sure we can do that cost effectively over its life. If we continue on, there's a lot of different pieces we want to consider in a good supportability plan. All right, there's sustaining engineering, supply support. So sustaining engineering means really we design this thing to operate in this operating environment. We're going to change that operating environment. What do we got to do different to support it? Supply support. Where are we going to get our parts from? How quickly can we get them? Are they staged strategically through the globe, or are they all coming from a single warehouse in a single location? Those are things we need to manage. We're also looking at technical data. What technical data do we need to support these assets? I don't know how many organizations I go to, and they don't have drawings, bills of materials, those types of things for assets, yet it's a huge, huge part for maintainability. Also, what type of manpower and personnel is required to support that asset? Want to identify all those, and that's coming from the maintenance task analysis. So we can make sure we get our maintainers in place before the actual activity begins. All right. Now, all this comes out with an integrated logistics support plan. All right, and we're not going to get into the details of that, but it considers all these different elements. If we continue on, we also have to think about where and how maintenance, or who and where will the maintenance be performed. For example, if we look at the U.S. Air Force as an example here, we have all the different bases down here where the F-35 is scheduled to be deployed at. So that is the organizational or front level activities that will be done at those bases by the maintainers. They're going to be involved with, troubleshooting, adjusting, calibrating, remove and replace type activities. But they're not going to be doing all these different things on the F-35s as an example. there's certain depot level or intermediate level activities that will be taking place. At the intermediate level here, they will be sending certain things there to be done. So if they removed and replaced this modular unit, they'll likely send it to one of these other locations for more specialized disassembly, troubleshooting, calibrating, so on and so forth, to perform those repairs. And then if they can't do it at the intermediate level, it may go to the depot level where very specialized complex repairs are performed. All right, so we want to understand who's going to be doing what. Now, some organizations might not be sending stuff to different locations, but what they will do is the organizational level are their internal maintenance staff. The intermediate level would be when they bring in an OEM or subcontractor for a very specialty task, and so on and so forth. So you can separate it that way as well, not just physical locations, but also skill sets and contractors. It's important to understand because then you can start predicting how much am I going to have to spend to maintain this asset over its life. Getting close to the end here, but next thing we got to do is we got to develop that maintenance plan. So how do we do that? Well, this would probably seem pretty familiar to everyone here. We got our asset design, performance requirements, operating environments, and we're going to feed all that into an RCM analysis. We're going to get that RCM analysis for repairs, for preventative, corrective, and so on and so forth activities. And there we'll do our maintenance task analysis like we looked at previously. From there, we can identify everything we need to support that asset throughout its life before it even arrives on site. From there, we get our larger maintenance plan and how we're going to maintain this asset throughout its life. Now, there's a lot of things there that you can get into huge amounts of detail, analysis, and so on and so forth. But let's talk about some practical maintainability considerations, because I'm willing to guess many of you are in the situation I found myself in multiple times where we don't have time to do a lot of that. But what are the easy things we can ask the design team about to make sure that we're getting something that's easily maintained? First area I want to talk about is the ease of maintenance. How do we make maintenance easier for our team? Use of remote lube lines or auto lube units, something we can do. So that way we can lubricate while it's running. Use of automated data collection systems for condition-based maintenance. Instead of having to do routes or access places that might not be that safe while it's running, and so on and so forth. Can we leverage that? Can we standardize assemblies with quick change connections? When I was in the machine building business, we did a couple of robots initially, and when we wired the wiring harness for those things, they were hardwired into the panel and to the tooling at the end. Next evolution, those were all quick connects. So if that cable assembly failed, we pulled off the cable assembly, put the new one on. Made it a lot easier for both our customers to stock and to perform repairs. Can we use some visual factory approach for visual inspections? Red, green, yellow on oil reservoirs and so on and so forth. Can we do those types of things? And then this one here is, can we put replaceable or serviceable items at 100% higher than the minimal functional requirements? What do I mean by that? So for example, if we have a filter, can we put in a second filter beside it so we can bypass one, perform the maintenance on it, and switch over to the next one? Right? We can use it with filters, screens, battery supplies, and so on and so forth. We can do that for a variety of things, but that way we're supporting the asset without taking away the availability. We also want to consider, how do we reduce diagnostic time? Can we automate some of the fault detection and isolation tasks where possible with built-in testing? Can we have built-in troubleshooting guides, right? Whether it's a documentation or electronically, can we have those built in? How do we simplify the design as much as possible? This next one is a huge pet peeve of mine, being an electrician. All the sensors should be tagged, all right? I don't know how many times you see sensors out in the field and none of them are actually tagged with the input-output number or anything like that. And as a result, troubleshooting becomes very, very difficult. Is there a way to provide notifications to lots of operational redundancy to the operating crew? Those are things we want to consider and ask the design team. Can you do this? Have you considered these? May also want to look at, how do we standardize spares? Can we provide redundancy for high failure rate items or long repair items, long time to repair items? How do we do that? Is that possible? Yeah, it may cost us a little bit more up front, but overall it'll do this for the life of the asset. Next, we want to consider improving equipment accessibility. How do we ensure the equipment has clear access around it? Is there a smooth grade around that asset if we have to set up scaffolding or lifting devices? Are isolation points located nearby so we're not having to walk half a mile down the road or half a kilometer down the road to isolate something before we work on it? Is there adequate lighting? Is there reasonable room to access the equipment? And then how do we speed up recommissioning? So if we do perform a repair, is there a built-in self-test that the equipment can run through before we start it up? That way we verify it's going to operate as expected. Those are types of things we want to do. All right, Rupesh, will TPM help with this? TPM may help with it. You may want to build that into your larger maintenance plan. If we're leveraging visual inspections, those types of things, it will help a little bit. But really, most of this stuff is focused on the design side of it. To be honest, if you want to get really good at this, it's design changes that's going to make or break the success of it. Some of the other things we want to see, reducing the actual repair time. Ensure, maintenance support services are available. Do we have electrical outlets, air connections that are accessible at those work locations? How do we reduce or eliminate the need for specialized tools or equipment? Can we eliminate the need for soldering, welding, brazing, and so on and so forth, and provide those connection points? And then provide those lifting facilities, lifting points, and so on and so forth. And then can we eliminate administrative tasks? So one facility I worked at, you had to get a man lift or scaffolding for everything. The next site had stairs, platforms, all those things built in. So we eliminated the need for all these working at height permits. Can we do that? And that's once again going to have a huge impact on reducing our mean time to repair, which improves maintainability. All right, Neil, how can we put these items as requirements or standardize them to the OEM that produces the equipment? Great question. The organizations I've seen successful with this, they actually build it into their requirements documentation within the procurement process. So if they're not building it on their own, they'll actually have all these requirements listed out, including what documentation do we need, what format do we need that documentation. We need the copies of the FMEAs and so on and so forth. All those things are all listed out in the requirements document, and that's built in as part of the procurement contract. If it's not in the procurement contract and it's not called out specifically, I don't think you'll have a lot of success with it. The only way I've seen it successful is leveraging, that cross-functional group between engineering, procurement, and so on and so forth to get these things in place. So this was a huge overview. There's a lot more detail. So this book here, I authored 5 chapters, contributed to 2 others. It is a great book on all the different aspects for maintainability. It is a huge resource. It covers everything we covered here in detail, plus a whole lot more. In the back, it includes a multi-page checklist for maintainability. We put some practical considerations there. I think there's a good 5 or 6 pages for various areas that you want to consider. And then obviously the book is how do you identify, evaluate, and go through those different things. You can get it on Amazon and Wiley and a bunch of other places. If you have any questions around maintainability, design for maintainability, let me know. I'll be more than happy to answer them for you guys. And with that, I'll open it up for questions. Anyone have any questions or anything I can help with?
I think you did an awesome job grabbing all of the questions as you went, worked it in really nicely. So thank you so much, James, for that wonderful conversation presentation. And thank you to the audience for asking some great questions. I just want to double check that you saw the one from Francisco over in the questions tab.
Yes.
Okay, great.
Yep, I did get that one.
I missed that one, sorry.
All
right.
Well, if there's no other questions, feel free to reach out to me in the Slack group, or you can reach me with the contact information on the screen. I'll be more than happy to answer everything. Oh, another question came in.
Yeah, we got one more.
Israel, what about the equipment that goes obsolete? How do you improve to the equation of maintenance? Great question. That's one of those supportability things that you got to understand, that electrical equipment is going to go through an obsolescence phase. So then we have to understand, do we want to buy more and stock more ahead of time? But then we have risks of dealing with firmware updates, things failing in the storeroom, those sorts of things. And if we don't want to address those, then what we have to do is have that sustaining engineering plan in place that says, when these go obsolete, what do we want to do about it in the future? Are we going to move to this, or how are we going to make that decision, and so on and so forth? So that's all laid out in that sustaining engineering piece. But it is a huge piece of huge consideration, especially at the rate of obsolescence that we see.
I see another one over in the questions tab. Reads, in cases such as the manufacturing technology of internal combustion engines and the arrangement of accessories such as the starter motor, can we say that the introduction of these technologies have affected maintainability? How laborious it is to perform maintenance on them?
So there is a huge piece to that, Francisco. I opened the hood of my wife's car and I can't identify anything, let alone reach in to get some of the components out of there. Whereas my old truck, there's still lots of room to grab stuff. That is a huge issue. Now, obviously, as things become more reliable, there's less of a focus on the maintainability side, because we would be performing less repairs. And I think that's where that design trade-off comes in. It's much more reliable. Do we want to make it a little bit harder to maintain to save costs, save space, and so on and so forth? And that's what that design requirements and the design requirement evaluations are really doing, is trading off those different pieces. And unfortunately, for certain machines, assets, that's not something we can have an influence on. We're not going to influence Ford or General Motors or Mercedes or them on those types of things. But for the larger one-off assets that we buy, I think we can have an impact on that.
Awesome.
Looks like another one from Denny.
Yeah.
Life cycle of the equipment influences the type of maintenance that we could adopt. Yes. If it is a very short life cycle, it's only going to last for a year or two and then we're going to get rid of it, we're going to have a very different maintenance plan than if it's a passenger aircraft that we want to operate for 25 or 30 years. So that life cycle will have a huge influence on the maintenance plan that we're going to have.
Awesome. Well, I think that gets us through our questions. As Jay mentioned, please feel free to reach out to him with his contact information here or in the Slack community. You're pretty active on LinkedIn as well. So really an available resource for all of us here. Thank you again for your time, James, and everyone for attending. And we'll put a pin in it, and I'll see you next time.
All right. Thank you.
Awesome. Thanks so much. Bye.